Hello everyone, my name is Mary Lou Raduban. I'm one of the lecturers in 124103 Biophysical Principles. In this video, I will be talking about freefall. And at the end of this video, you would be able to recognize and analyze freefall problems. I will also discuss some of the mathematical tools and skills that we will need as we study this course. Some of this you have already encountered, for example, using the correct units and to some extent unit conversion, but we'll go more into detail about unit conversions in this video. We will also learn how to convert units and how to write numbers in scientific notation. So in the past videos, we've been talking about motion and describing how an object moves. We learned about acceleration. It's how fast velocity changes over time. Now, Galileo performed an experiment with a ball rolling down an inclined plane, and he noticed that when a ball rolls down a slope, its speed increases. In short, its velocity is changing and therefore it has acceleration. Now, he increased the inclination of the inclined planes and he noticed that steeper inclines gave greater accelerations. And in fact, when the incline was vertical, acceleration was maximum, and it's the same as that of an object that's falling. When air resistance is negligible, all objects fell with the same unchanging acceleration. This motion, where the objects fall with constant acceleration only under the influence of gravity, and there is no air resistance, or at least air resistance is negligible, is called free fall. So in free fall, the objects have a constant acceleration, it's the same, and the objects fall at the rate of 9.8 meters per second every second, or that's 9.8 meters per second squared on the surface of the Earth. Sometimes it's convenient to use 10 meters per second squared instead of 9.8 meters per second squared. So under free fall, when there's only the influence of gravity and air resistance is negligible, the acceleration of the object is constant, and we indicate that by the variable g. So the constant acceleration under free fall is g, and that's equal to 9.8 meters per second squared, or to make calculations more convenient, we can round that to 10 meters per second squared. Because all objects fall downwards due to the influence of gravity, the direction of acceleration is always downwards. And if we define the downward direction to be negative, then the acceleration will be equal to negative g, and that will be negative 9.8 meters per second squared, or negative 10 meters per second squared. All right. So let's test out our conceptual understanding of free fall. So you have three stones. One stone is thrown upwards, one is thrown downwards, and one is released from rest. After the stone has left your hand, which stone experiences the greatest acceleration if we assume that friction is negligible, so that the stone only falls under the influence of gravity? If you answered that the stones will all have the same acceleration, then you are correct, because any object that's falling only under the influence of gravity and friction is negligible will be falling under free fall. And its acceleration is constant, that's equal to the gravitational acceleration g, which is negative 9.8 meters per second squared, meaning every second the velocity of that object changes by 9.8 meters per second. It's a little bit difficult to visualize that, because sometimes when we drop a stone and a feather on the surface of the earth, we'll see that the stone falls faster than the feather. But that's because air resistance is not negligible under that experimental condition. Now watch this video where they simulated the conditions for free fall and air resistance is negligible.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems, and that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of, so they built an outer concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space. Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So, in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCB 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4, cameras on, 2, 1, release.
Look at that.
They came down exactly the same. Wow.
Look. That's right there. Oh, they hit right there.
Exactly.
Back on the side.
Exactly the same.
Feathers don't move, nothing.
Look at that. That's just brilliant.
Okay, so we can see in that video there that regardless of how heavy the object is, they fell to the ground at the same rate, meaning their speed increased at the same amount, with the same amount, and therefore they had the same acceleration. And that acceleration is the gravitational acceleration, g. So the fact that they had some acceleration, we can measure then they have some velocity that's changing, and the velocity of the object in free fall we can calculate using this kinematic equation which we learned in the previous videos. except that under free fall, the acceleration is gravitational acceleration, and that's negative g. So the negative sign, so notice how we changed the positive sign in the kinematic equation to a negative sign, and that's because the direction of acceleration is always downwards during free fall. So remember that velocity is a vector, meaning the direction is important. So you need to include the sign of the velocity to indicate the direction. So if the object is initially thrown upwards, then the sign for the initial velocity should be positive. If the object is initially thrown downwards, then the sign for the initial velocity should be negative. And if the object started from rest, then the initial velocity should be 0. Okay, so let's analyze free fall further to sort of understand it more conceptually. And let's consider the special case when the object started from rest and Vi is equal to 0. So for an object starting from rest, Vi is equal to 0, and under free fall with negligible air resistance, when acceleration is 10 meters per second squared, what will be the velocity after 1 second? And what will be the velocity after 2 seconds, after 3 seconds, and so on? Can you sort of come up with what the velocity will be after 1 second, 2 seconds, and 3 seconds? All right, the acceleration is 10 meters per second squared. That means that every second, velocity changes by 10 meters per second, which means that after 1 second, the velocity will be 10 meters per second, but the direction is downward, so you have the negative sign there. After 2 seconds, the velocity would have increased by another 10 meters per second. So after 2 seconds, the new velocity will now be 20 meters per second. That's negative because the direction is again still downwards. After 3 seconds, the velocity is negative 30 meters per second. After 4 seconds, the velocity will be negative 40 meters per second, and so on. So you get the picture there. You can calculate that using this equation, but you get the same thing. It's just a conceptual understanding that because the acceleration is 10 meters per second, that means that velocity changes by 10 meters per second every second. Okay. Now, if we're talking about speed, speed does not need direction. It's a scalar quantity. And so we just disregard the negative signs because the negative signs here tell us that the object is falling, it's moving downwards, and we've taken downwards as the negative direction. So for speed, after 1 second, the speed of the object would have increased to 10 meters per second. After 2 seconds, the speed would have increased to 20 meters per second. After 3 seconds, it's 30 meters per second. After 4 seconds, it's 40 meters per second, and so on. So when moving downwards, the speed increases by 9.8 meters per second, or more conveniently, 10 meters per second every second. So that's sort of what acceleration equals 10 meters per second squared means. Every second, the velocity changes by 10 meters per second. All right, let's test out our conceptual understanding. And we have here a problem which says that a free-falling object was dropped from rest and it had a speed of 30 meters per second at 1 instant. Exactly 1 second later, what will be its speed? I'll give you a few seconds to sort of think about this question and come up with an answer, and then we'll look at the answer and the explanation for that. All right, so if you answered that the new speed 1 second later would be 40 meters per second, then you'd be correct. Yeah, you can calculate that using the equation for speed, which is acceleration times time. But acceleration will be equal to gravitational acceleration. And here we use the approximation 10 meters per second squared for the acceleration. But also, you don't have to do this calculation if you know that the acceleration is 10 meters per second squared. Then you know that every second the speed will increase by 10 meters per second. So when moving downwards, the speed increases by 10 meters per second every second. Or if you want to be more precise, the speed increases by 9.8 meters per second every second. Right, how about for this scenario where a ball is thrown vertically upwards with an initial speed of 30 meters per second? So instead of falling from rest, there's an initial speed of 30 meters per second. In which direction is the ball moving after 2 seconds? Again, we can assume negligible friction so that the object is undergoing free fall. Yeah, I'll give you a few seconds to think about this problem again, and then we'll look at the solution. All right, so if you answered that the ball is moving upwards, then you would have been correct. And you can figure that out by either calculating using this equation. Given that the initial velocity is 30 meters per second, the gravitational acceleration, you can sort of use 10 meters per second squared as approximation. And you want to find the velocity, the final velocity after 2 seconds. And sort of once you know the final velocity, if it's positive, so if it's a positive final velocity, then the object is moving upwards. Okay, and if you calculate a negative final velocity, then that tells you that the ball is moving downwards. So you can do that approach, okay, or you can answer this question conceptually. So you know that the ball started from here, it had an initial velocity of 30 meters per second, and it was thrown upwards. Okay, friction is negligible, so even though the ball is moving upwards initially, it's still undergoing free fall, meaning its speed, because it's going upwards, its speed will decrease by 10 meters per second. Okay, so after 1 second, okay, initial velocity is upwards. After 1 second, so this is time equals 0 will be the time when it's thrown upwards. After 1 second, okay, because the ball is going upwards, its speed would have decreased by 10 meters per second. Okay, so its new speed will be 20 meters per second. If you consider velocity, that will be a plus 20 meters per second to indicate the direction because your object is still going upwards. Okay, after 2 seconds, 2 seconds after the ball was thrown, 2 seconds, okay, acceleration is still 10 meters per second squared. That means that the velocity is changing by 10 meters per second every second, right? So your so that's the initial velocity. So let's just call this velocity. So after 2 seconds, your velocity will be plus 10 meters per second. Okay, the speed has decreased by 10 meters per second because the ball is going up. The direction is still upward, so you have this positive sign for the velocity to indicate that the direction is upwards. Okay. After 3 seconds, at t equals 3 seconds. 3 seconds after the ball was thrown. Okay, the acceleration is still 10 meters per second squared. It's constant under free fall, which means that the speed would have decreased by another 10 meters per second. So at this point, the new speed will be 0. Okay. So you can see here the pattern. Initially, it was thrown at 30 meters per second. After 1 second, the speed decreased by 10 meters per second. So it's now 20 meters per second. The velocity is still pointing upwards, so you have that positive sign. After another 10 seconds, the speed decreased by another 10 meters per second. And after another second, the speed has decreased by another 10 meters per second. So at this point, at 3 seconds, the ball now has a speed of 0 meters per second. So it stops momentarily. And then, okay, and then the ball starts to go down. Okay. So from this top position here, the ball will start to go down. Okay. And so at t equals 4 seconds, it would be like dropping a ball from this height, starting from rest, starting from 0 meters per second. So after 4 seconds from the initial release, okay, the velocity will now be negative 10 meters per second. Okay, it's now negative because your ball is going downwards. Okay, a second after, which will be 5 seconds since the ball has been thrown, the velocity would be negative 20 meters per second. Okay. And then after a second later, t equals 6 seconds from the time the ball was initially thrown, the velocity will be negative 30 meters per second. So you can sort of see the pattern here that because acceleration under free fall is constant and it's 10 meters per second squared, the speed changes by 10 meters per second every second. If the object is going up, then the speed decreases by 10 meters per second every second. And if the object is going down, then the speed increases by 10 meters per second every second. Okay. So this essentially summarizes the text in this box here, essentially summarizes the idea of how the speed changes every second if the object is under free fall. Right, so how about the displacement? How far the object travels when in free fall. So we can use this equation for displacement from the kinematic equations that we learned in the previous lessons, except that again the acceleration is changed to gravitational acceleration g, and the sign is changed to negative. So the original kinematic equation is vi plus 1/2 at squared. Okay. But a, we replace that with g, gravitational acceleration, and because gravitational acceleration is always directed downwards, okay, this sign will be negative to indicate a downward direction. Okay, so again, remember that velocity is a vector. So just like incorporating the direction for gravitational acceleration to be negative, you also need to incorporate the sign for your initial velocity here. As we've said earlier, if the object is initially thrown upwards, your initial velocity will be positive. If your object is initially thrown downwards, then the initial velocity should be negative. And if the object starting from rest, then of course the initial velocity will be 0. Okay, so for an object released from rest, you have here this vi is just equal to 0. And so the displacement after 1 second will be negative 5 meters. Because if we work out this equation here, the displacement is equal to negative 1/2. So here I'm again using the rounded form for gravitational acceleration, which is 10 meters per second squared for convenience. Okay, so that's 10 meters per second squared, and after 1 second, t squared is 1 second squared. Okay, work that out. You have a displacement of negative 5 meters after 1 second. If you work out the displacement after 2 seconds, then you just replace the time to 2 seconds. Okay. If you're working out the displacement after 2 seconds, and you'll get negative 20 meters after 2 seconds. So note again here the signs. You have negative signs here, which means the displacement is downwards relative to the starting point. So we've taken downward direction to be negative direction. For distance, if you just want to calculate the distance, distance is a scalar quantity, so you don't need the direction. So you can simply disregard the signs, okay, and have only positive values for your distance. So here also we disregarded the sign, the negative sign, in order if you just wanted to get the distance. All right, so try this problem out. You have an object that's undergoing free fall. It started from rest. What will be the distance traveled by the object after 4 seconds from the time that it started from rest? Right, so unlike for velocity and speed, which we've answered the questions for using conceptual reasoning, for the speed, for the distance and displacement, you sort of really have to calculate that using this equation. So for this problem where you're wanting to find the distance after 4 seconds, then you have to substitute 4 seconds for the time there. Distance equals 1/2 gt squared. 1/2 multiplied with the acceleration due to gravity multiplied with time. So t squared means that you need to multiply with time 2 times. I'm using again the approximation for g, which is 10 meters per second squared for convenience. And the time is 4 seconds because we want to find the distance after 4 seconds. And we do get a calculation of 80 meters. All right. Okay, so that's the idea behind free fall. In free fall, the object is moving only under the influence of gravity with negligible air resistance. So the acceleration is constant at 9.8 meters per second squared or 10 meters per second squared, and the direction is always downwards, so you have a negative acceleration there. The speed changes by 10 meters per second every second, and for the distance you need to calculate that using the kinematic equations. And we've been calculating numbers and talking about physical quantities in physics so far, and you've noticed that every time we've calculated something, we indicate the unit. So for example, here 80 meters tells us that that's a number relating to distance. Okay? And so when describing any physical quantity in physics, units are very important. Quantities without units have no meaning, because if you just say 10 or 5 without indicating the unit, you're not sure whether that means 10 seconds or 10 meters or 10 apples, or or 10 meters per second squared. So we always need to indicate the unit. So you have the number and the unit that's indicated. Okay, so for example, time, when we say 60 seconds, that means there are 60 times 1 second in the time of 60 seconds. 50 kilograms means 50 multiplied by 1 kilogram, and so on. So as we learn different physical quantities in this course, we will encounter different units, and we already encountered some of them. For example, the unit of length is meter. The unit of time is seconds. Soon, when we go to forces in the next lecture, we will encounter mass, and the unit for mass is kilograms or kg. Later on in the course, we will be talking about temperature, and the SI unit for temperature is Kelvin, capital K. I think for these 3 units, we will not use them so much in this course, but it's just good to know these base units for these quantities as well. We've also encountered what we call derived units. Derived units are what we obtain by combining base units. For example, we are calculating the area under a graph to determine the displacement from a velocity time graph. And so we're multiplying 2 lengths. Okay, so the unit for that area will be meters squared because we're multiplying 2 lengths, and the base unit for length is meters. So meters multiplied with meters will give us meters squared. Velocity is also a derived unit. Velocity is defined as displacement over time. Displacement is a quantity of length with a unit of meters, and time is and you have time, which has a base unit of seconds. So in deriving the quantity of the unit for velocity, you simply substitute the unit in the equation. So you have meters divided by seconds, or meters per second. And you can also write down this notation meter bar second as meters second to the minus 1. So as we progress in this course, we'll encounter many other derived units, and at least you know that derived units are determined by substituting the base units in the equation for that derived unit. Sometimes we'll also abbreviate powers of 10 using prefixes. This is especially useful if we're talking about big numbers that are multiples of 10. And so we have unit prefixes that are added to the base unit. So some common prefixes that you're probably familiar with is kilo. And kilo, it has a symbol of small k. That means 10 to the 3 or 1,000. Milli, okay, which is a symbol of small m, and that's 10 to the minus 3, or 1 over 1,000. There's one here that's sort of missing, which is also common, which is the centi, abbreviated by small c, and that's 10 to the minus 2, or that's 1 over 100. So prefixes are added to the base unit. So when we say 1 kilometer, the prefix is kilo, which is 10 to the 3. So 1 kilometers is 1 times 10 to the 3 meters. So notice there, kilo is 10 to the 3. Okay, from here, kilo is 10 to the 3. Millisecond, 1 millisecond means 1 times 10 to the minus 3 seconds. Okay, because milli, the prefix milli is 10 to the minus 3. That's milli, and that's 10 to the minus 3. All right, so 1 millisecond is 1 times 10 to the minus 3 seconds. Okay. Many times we will encounter units that are not in base units. For example, we encounter units of distance in kilometers, and we want to convert that to the base unit meter. Or we encounter unit of time in hours, and we want to convert that to the base unit of second. And so the other skill that's very important in this course is unit conversion. And I think unit conversion is also, say, for example, you want to convert money. How many British pounds are there in a certain amount of New Zealand dollars? Then you need to convert between New Zealand dollars and pounds to know how many pounds are there in a certain amount of New Zealand dollars. So in unit conversion, one important thing to remember is unit conversions involve a conversion factor. The conversion factor relates the two units that are involved. So in this case, if we want to convert pounds from pounds to New Zealand dollars, then we need to have a relationship between pounds and New Zealand dollars. So in this case, 1 pound is equal to 2 New Zealand dollars, or we can rearrange that so that $1 is 0.5 pounds. We arranged that by simply dividing this by 2, because we want to have $1, and any number divided by itself is equal to 1. So if we divide $2 by 2, we will have $1. But whatever you do on one side of the equal sign, you have to do on the other side as well. So 1 pound divided by 2. Okay, 1 pound divided by 2 will give you 0.5 pounds. Okay, and $2 divided by 2 will give you $1, because any number divided by itself is equal to 1. Okay, so you have these two forms of the conversion factor. 1 pound equals $2, or $1 is equal to 0.5 pounds. So if we wanted to convert 500, $500 into British pounds. Let me just erase this. Oh, it also erased everything. Okay, so if we wanted to convert $500 into British pounds, how do we go about converting dollars to pounds? Okay, so the first thing you need to have is a conversion factor, which we already have here. Okay, the next thing you do is to write the number in terms of the number and the unit. Okay, so here we separated $500 into 500 pieces of $1 notes. Okay, and then you substitute the unit that you don't want with the unit that you want using the conversion factor. So you don't want the dollar, you want the pound, and you know that your conversion factor tells you that $1 is equal to 0.5 pounds. So we change $1 with 0.5 pounds and do the calculation and see that $500 is equal to 250 pounds. Okay? Right, let's do another conversion, and hopefully that will become clearer. Okay, we want to convert 40 inches to centimeters. You know that 1 inch is equal to 2.54 centimeters. So how many centimeters are there in 40 inches? Right, I'll give you a few minutes to try and solve this by yourself, or you can pause the video and come back, and then we'll look at the solution. All right, so the first thing to do is to write down the conversion factor, because the conversion factor relates the two units that are involved. inches and centimeters. It gives you a relationship between these two, which allows you to convert inches to centimeters. The conversion factor is 2.54 centimeters is equal to 1 inch. Okay. And then you write your number in terms of the number and its unit. So 40 inches can be broken down as 40 times 1 inch. By doing so, you can clearly see here 1 inch, which is the unit that you want to replace. And you relate that to your conversion factor, which tells you that 1 inch is equal to 2.54 centimeters. So you simply replace 1 inch with 2.54 centimeters. So 1 inch is changed and replaced by 2.54 centimeters. And then do the calculation, 40 multiplied with 2.54, and you get 101.6 centimeters. Okay. All right, let's try to convert something a bit more complex. We have here now a derived quantity, a quantity with derived units. We want to convert the area 25 millimeters squared into meters squared. Meters squared. How do we go about converting millimeters squared into meters squared? Okay, try this out on your own, and then we'll look at the solutions after a few minutes. Okay, we can break down 25 millimeters squared into a number and units. So 25 millimeters squared is essentially 25 multiplied with 1 millimeter multiplied with 1 millimeter. So note that millimeter multiplied with millimeter is millimeter squared. Similarly, if you do meters multiplied with meters, that's meters squared. Okay, so what we've done here is break down 25 millimeters squared into the number and the units. Then you have your conversion factor, okay, the prefix milli. Right, so this is the prefix, that's the prefix milli. Okay, and milli is 10 to the minus 3. The prefix milli means 10 to the minus 3. And so 1 millimeter is equal to 1 times 10 to the minus 3 meters. Okay, you essentially changed the prefix milli by 10 to the minus 3. But you still have the unit meter there that's carried over. So that's your conversion factor. And then you go back to your quantity and its units and replace the units that you don't want with the units that you want using the conversion factor. So 1 millimeter is equal to 1 times 10 to the minus 3 meters. So you replace that here. 1 millimeter equals 1 times 10 to the minus 3 meters. And you have to do that twice because you have millimeters squared. And then you do the calculation. Okay. And that will give you 25 millimeters squared. If you did it in the calculator would give you 2.5 times 10 to the negative 5 meters squared. Right, so that's the conversion for 25 millimeters squared into meters squared. So the important takeaway idea here is that if you're converting something that's squared, like millimeters squared, you need to convert millimeters 2 times. Because millimeters squared essentially is millimeters times millimeters. So you have to convert this millimeter and then that millimeter, and that's why you have to do the conversion 2 times. You have here the 2 conversions from millimeters to meters. Okay, so 2.5 times 10 to the negative 5 can also be written as 0.000025. Okay, it's quite a small number with a lot of zeros. Okay? And in fact, in science, there are lots of very large and very small numbers that you will encounter. For example, the speed of light is this 300 million meters per second. Okay. The size of a hydrogen atom is this small, 0. All of the zeros, 1 meter. Okay. The mass of the human cell has all of these zeros. Also, the age of the universe has many zeros. And you can see here that if you're dealing with these very big and very small numbers, it can get quite tiring and confusing writing all of these zeros. Okay? And so we need a clearer and easier way of reading and writing these very large and very small numbers. And that way is what we call scientific notation. So in scientific notation, we write the number as a number times 10 to raise to an exponent. Okay, where A is just a number that's between 1 and 10, and B is what we call the power or the exponent. The power must be an integer, a whole number, and it can be positive or negative. So for example, 3 or negative 7, but it cannot be a fraction. It cannot be 5 divided by 3 or a decimal 4.8, negative 4.8. So it has to be an integer. Whether it's positive or negative, it has to be a whole number. Okay. Right, so how do we get that number A and this power B? So to get the number A, you move the decimal place so that you have a number between 1 and 10. That number between 1 and 10 will be the number A. Okay, and then count the number of places that you move the decimal point to get the number between 1 and 10. And the number of places that you moved will give you the power in the scientific notation. And if you moved the decimal point to the right, then the power is negative. If you move the decimal point to the left, then the power is positive. Okay. So why don't you have a go and convert these numbers into scientific notation? So you have here the distance between Sun and Earth, which is a very big number, and then the mass of a hydrogen atom, which is a very small number. Right, so remember that the scientific notation is A times 10 to the B, okay, where A is a number between 1 and 10, and B is the number of places that you move the decimal point in order to obtain A. So let's do the first one. Okay. If it's just an integer whole number like this, okay, the decimal point is right at the end. It's not specified, but it's well known that the decimal point is right at the end there. So to get A, we move this decimal point. We need to move this decimal point to the left so that we have a number between 1 and 10. So you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. And you've moved the decimal point from the end to this position between 1 and 5. So you have there 1.5 will be A. Okay. So A is equal to 1.5, right? And then you moved 11 places to the left. So B is 11 jumps or 11 places that you move to the left. And since you move to the left, that will be a positive number for B. So you write down your scientific notation as 1.5 times 10 to the positive 11. Don't forget your unit in the end. Okay, so the distance between the Earth and Sun is 1.5 times 10 to raise to the power of 11 meters. Right, do that for the hydrogen atom. Okay, here it's a very small number, so it's sort of more obvious where the decimal point is. Decimal point is here. We need to move it so that we have a number that's between 1 and 10. Okay, obviously we need to move the decimal point to the right. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Okay, and we put our decimal point there because 1.67 is a number between 1 and 10. Okay, so our A is 1.67. Okay, and B is the number of places we move the decimal point for. That's 27. But we move the decimal point to the right, so that will be a negative 27. So we write our number, the mass of hydrogen atom, as 1.67 times 10 to the negative 27, and don't forget the unit kilograms. Okay. All right, so notice here, if you have a positive exponent, positive power, if you have a positive B, positive, let me write more clearly. If you have a positive B, that means that your number is greater than 1. And if you have a negative power or negative B, that means that the number that you've just written in scientific notation is less than 1. Okay. And that sort of gives you a clue. So if, for example, you're given this scientific notation, 1.67 times 10 to the negative 27, and you're being asked to convert that to a number instead of scientific notation, okay, the fact that B is negative, you have this negative power here, that means that your number should be less than 1. And so you move your decimal point to the left so that your number is less than 1. In this case, if you want to go from scientific notation to the number, look at the exponent, the power. Since the power is positive, then you know that the number should be greater than 1. And so you move your decimal point to the right so that you end up with a number that is greater than 1. Okay, all right. Okay, so those are the answers there, which we just worked out earlier. Okay, and essentially, that's this lecture here. We learned about free fall. It's the motion of an object under gravity only. The air resistance is negligible. And so the acceleration is called gravitational acceleration G. And it's constant. It's negative 9.8 meters per second squared. The negative tells us that the acceleration is always directed downwards. And when we're dealing with quantities in physics, we should always include a unit. Sometimes it's useful to work in base units, and so we need to do some unit conversion sometimes. And if we're dealing with very large and very small numbers, it's useful to write the number in scientific notation. Right, so that ends our lecture. I'll see you again in the next lecture, where we will now start to talk about forces.